Hi, in this module we'll continue talking about group level analysis. Here we're going into the more technical detail. We'll set up the models, we'll talk about how to estimate them, and how we move forward from there. Let's begin by going over some general terminology that we need when performing statistical analysis. Whenever applying statistics to a real-world problem such as neuroimaging, we need to separate between the model used to describe the data, the method of parameter estimation, and the algorithm which we use to obtain the parameter estimates. The model uses probability theory to describe the parameters of the unknown distribution thought to be generating the data. So the model is an idealized description of what's going on and what we're trying to understand. The method defines the loss function that's minimized in order to find the unknown model parameters. Finally, the algorithm defines the manner in which the chosen loss function is minimized. Let's start by talking about the model in the context of group level analysis. So when performing group analysis, we often use what's called a multi-level model. Most often this is performed in two different levels. In the first level, we deal with individual subjects. And in the second level, we deal with the groups of subjects. So here's a cartoon over what's going on here in the multi-level model. We have a kind of a nested case here where we have the group in the second level, and within the group we have a number of subjects in the first level. Now again, as we talked about earlier, this hierarchy can be made, we can make a third level, a fourth level as well, but for now let's concentrate on a two-level model. Again, all inference is going to be performed in the massive univariate setting. So even though we're looking at multiple subjects, we're still looking at a single voxel of the brain. In order to perform multi-level models in fMRI, several pre-processing steps should be applied prior to performing the group analysis in order to assure the validity of the results. And they include motion correction, which is intra-subject registration, spatial normalization, which is inter-subject registration, and spatial smoothing, which overcomes some of the limitations in spatial normalization. So motion correction is always important to perform whenever we're performing a GLM type analysis. Spatial normalization is very important in group analysis because if we're comparing two brains with each other, we have to make sure that they live on the same stereotactic space. So for example, if I'm looking at a voxel from my brain and a voxel from your brain, we want to make sure that those voxels are from the same brain region. So therefore our brains need to be normalized to one another before we perform group level analysis. Often there are some residual artifacts when performing spatial normalization, and therefore spatial smoothing is usually needed to get rid of those artifacts. So let's begin by looking at the first level model. Here we want to model each of the n different subjects. So let's begin by, for each subject, modeling their data according to a standard GLM. So we'll use the model yk equal to xk beta k plus ek, where ek is normally distributed with mean 0 and variance-covariance matrix vk. So this is a standard GLM model. The only difference between this model and the one we talked about a few modules ago is we have the index k here to represent that this is from a single subject k. Now we're going to have n of these models, one for each of the subjects. And so here's an illustration of what the design matrix for a single subject will look like. So we have like a boxcar here, a baseline, and these discrete cosine basis sets. So this is just like what we talked about earlier. The only difference is that now we specify that it comes from a single subject, K. So in the first level, we have autocorrelated data with a relatively large number of observations. So Y is a vector with length, a couple of hundred time points. We can put all the subjects' data together in the following way. So we concatenate everyone's time series. So y1 is a time series from a certain voxel for subject 1. y2 is the same from subject 2 all the way up to yn. So we just string them out into one long vector y. We also make a kind of a super design matrix X, which contains the individual subjects' Xi matrices in a block diagonal form. We also string out the betas for each subject and the error terms. And similarly, the variance-covariance matrix is combined in a manner similar to the design matrix. So we have in each block, in the block diagonal form here, in each block we have VI corresponding to the variance-covariance matrix of the ith subject. Now the reason we write it like this is mostly for bookkeeping purposes, but if we do this, we can write the full first level model as follows. Y is equal to x beta plus E, where E is normal with 0 and variance covariance matrix V. So this is modeling simultaneously every subject. However, it is important to note that this model is separable and it gives the same results as if you were to fit each subject's data individually. The only reason we write it this way is, again, for bookkeeping purposes. So that's the first level model. Now the second level model can be written in the following way. Now we move the betas from the first level up to the second level, and we use this as our response variable. So the second level model is beta equal to xg beta g plus eta, where eta is normally distributed with mean 0 and variance covariance matrix V of g. Here x of g is the second level design matrix, and so this, for example, can be used to separate cases from controls, and beta g is the vector of second level parameters. So for example, let's assume that we had 4 subjects, 2 cases and 2 controls, and we assumed that the cases had a certain beta value, which we're going to call beta g naught, and the controls had a certain beta value, which I'm going to call beta g1. If I wanted to set that up in a second level format, I would write the design matrix and the betas as seen here on the right. So this will tell me that the first 2 subjects have mean beta g naught, and the second 2 subjects have beta g1. Now there's also an error on top of that. Another way we could set up the second level design matrix, if everyone was from the same group, we could just make xg be a vector of 1s, and we have a single beta g corresponding to the population mean. So in the second level model, we usually have IED data, so we assume that the betas from different subjects are independent of one another. However, we have relatively few observations. We might only have, say, 20 subjects or so. So the second level relates the subject-specific parameters contained in beta to the population parameters beta g. So it links the individual subject's data to the population from which the subjects were drawn. And so what it does is it assumes that the first level parameters have been randomly sampled from a population of possible regression parameters. And because we make this assumption, this allows us to generalize the results to the whole population. We can illustrate this model in pictorial form as follows. Let's suppose that we were performing a hypothetical experiment. Let's say that we were flashing a light in somebody's eyes repeatedly, and we were interested in estimating beta, which is the amplitude of the response. Now let's suppose that we were also interested in studying a certain population of subjects, and consider that we were able to perform a census of everyone in the population. So we were able to perform this experiment on every subject in the population and estimate their individual beta value. If you were to do that, we could make a population distribution of the beta values, and it might look something like follows. According to our model, we say that this distribution should be normally distributed with a mean beta g and a variance covariance matrix given by sigma squared g. This is our model. This is our idealized description of what we believe the population looks like. In reality, we don't perform a census. However, we can still keep this model. What we do is we take a random sample from this population. So let's say, for sake of argument, that I randomly sample 7 subjects from this population, and with that I randomly sample their corresponding beta values. And so their beta values are these x's. So this is a random sample, and because this follows a normal distribution, I would expect 68% of the samples to lie within 1 standard deviation, 95 within 2, and almost all within 3 standard deviations of beta g. We can look at these guys and see what these samples mean. So I'm going to twist this distribution to its side as follows. And so let's look at an individual person here. So if I look at this guy, and this is beta 1, this is the first person that I sample from this population. He was a low responder, so he's on the lower tail of the distribution, so he's significantly below the mean. So looking at him, and looking at what this means is that his response is lower than what we would expect from the population. So pictorially, we will get somebody with a rather low response compared to the noise, perhaps. This fellow here, which we'll call beta m, he's a high responder. He responds higher than average. So if we were to look at his response, we would get a more robust signal. So basically, this is what our multi-level model is doing. We're saying that each subject has its own beta value. In this case, beta 1 is going to be small, beta m is going to be large. And in order to link them together, we assume that they're drawn from a larger population, and that larger population is normally distributed with beta g and variance sigma squared g. By doing this, we're linking the first level model, where we're analyzing the fMRI time series, to the group level. And by doing this, we can also perform all our inference on the parameters of the group level. So we can test a null hypothesis that beta g is equal to 0, and this is basically a question about whether or not the population mean is equal to 0 or not. So by doing this, we've been able to move our inference from the individual subject to the population, and thus we can generalize it to a larger amount of people, even people that we haven't seen, because we've modeled the variation and that it took to sample those subjects. So we can summarize this two-level model as follows. So the first level is the concatenated data, and that's y is equal to x beta plus e, where e is normally distributed with mean 0 and variance covariance matrix V. And the second level model is linking the individual subject's beta to the group beta. And so this is the sampling from the population. So here we have beta is equal to xg beta g plus eta, where eta is normally distributed with some mean 0 and some variance covariance matrix V of g. Now, this model can be expanded further to incorporate more levels if we like, but most often we keep it at 2 levels in fMRI. This two-level model can be combined into a single model as follows. We start out by writing y is equal to x beta plus epsilon, but we know that in the second level that the beta is equal to xg beta g plus eta, so we can replace that, and we can write it in the following format. So what we can write is that now y is equal to, it's normally distributed with some mean xxg beta g, which is sometimes called the fixed effect, plus some random effects, which depends on v of g and v. So that's the model that we're going to try to estimate. The next step that we need to do is we need to figure out how to estimate it. So we have to figure out a loss function. What constitutes an optimal beta g, vg, and v in this case? So statistical techniques define the loss function that should be minimized in order to find the parameters of interest. And the most commonly used techniques include maximum likelihood and restricted maximum likelihood. So remember, we talked about that a few modules ago as well. Now, algorithms define the manner in which the chosen loss functions are minimized. So once we have the model and we have a criteria for what it means to get the optimal parameter values of that model, the algorithm will define the manner in which we find those parameters. And commonly used algorithms include Newton-Raphson, Fisher scoring, the EM algorithm, or Eagles and Wriggles. Let's go back and look a little bit at the difference between maximum likelihood and REML. So maximum likelihood maximizes the likelihood of the data. It produces biased estimates of the variance components. Restricted maximum likelihood maximizes the likelihood of the residuals, and this produces unbiased estimates of the variance components. So if we're interested in estimating variance components, we often use restricted maximum likelihood to define our loss function. Algorithms, well, the classic algorithm to find the solution to some optimization problem would be to do something like Newton-Raphson. This is an iterative procedure that finds estimates using the derivatives at the curved solution. Fisher scoring is a variant of Newton-Raphson, which finds estimates using the so-called Fisher information. And the EM algorithm is a more recent approach that finds estimates from models that depend on unobserved latent variables. So in this case, this could be the second level error. Different neuroimaging software packages have all implemented these mixed effects models, and they differ in which method and algorithm that they apply. However, in practice, a simple non-iterative two-stage least squares approach is most commonly used in fMRI data analysis. This approach is called the summary statistics approach. And so in the summary statistics approach, results from individual subjects are reused in the second level, and this reduces the computational burden of fitting a full mixed effects model. So what people do is they fit the individual level model and then reuse that at the second level. To summarize the summary statistics approach, we first fit a model to each subject's data, and we might construct contrast images for each subject. But let's just say, for sake of argument, that the contrast is just the beta corresponding to the visual stimuli in our example. What we do then is we conduct a t-test on the contrast images, and so in this case only the contrast are recycled from the first level and not the variance components, and so only one contrast can be estimated at a time. So basically what I would do is that for a single voxel I would take the beta value from all the subjects in the sample and just perform a t-test on that, and I would get a test statistic for that voxel. And I would do that for every voxel of the brain. Now this approach makes certain assumptions. It assumes that we have homogeneous intra-subject variance, and also that we use balanced design, so we have the same design matrix. Now analyzing data in this manner significantly simplifies the analysis, because what we're really doing is we're just doing a series of single subject GLMs and then combining them by doing a t-test across images. Now this is much easier than doing a full mixed effects model. However, again, we don't appropriately take into consideration the within subject variation. So this could give rise to some problems in certain situations. However, this remains by far the most dominant approach towards analyzing group level analysis because of its simplicity and ease of use. Okay, so that's the end of this module. Here we've talked about multi-level modeling, we talked about that simple two-level model, we talked about how to estimate the parameters. We also talked about the summary statistics approach, which is the dominant way of analyzing these two-level models. In the next module we'll talk a little bit about multiple comparisons. Okay, I'll see you then.